We'll be splitting Experiment 4 of Make Electronics 2nd edition by Charles Platt into two parts. It's a long and significant chapter, and it's centered around the idea of variable resistance. Now in the last experiment, we had made the circuit shown here. A first circuit which just lit an LED, and we found that the brightness of the LED depended on the current going through the circuit as determined by the value of the resistor. 2.2 kilo ohms was a little bit dimmer, 1 kilo ohm a little bit brighter. Today we're going to find out how we can have a whole range of variable resistances rather than just the discrete resistor components. One thing you are going to need is a 470 ohm resistor that's yellow, purple, brown, and with probably a gold stripe, and then a potentiometer. You have two of them in your box. They're either 1K or 2K. I'll be using the 1K today. Following the textbook, the 2K may also be in some kits. You'll need both of your potentiometers in all likelihood, of course, as well as your ohm meter and a few alligator clips. Now, not powering up the circuit. Remember, we're not adding power, we're just measuring resistance here. Flip your meter over to the 2K setting and measure across the outer two leads of this potentiometer. Remember, it's got a knob that turns. What I want you to observe is that you'll read some value, in this case 1.105 thousand ohms, no matter where I turn the knob. And it's only when I measure from one of the center pins to an outer pin. So here, for instance, on the right two pins, that I actually see the resistance change as I move the knob. And in fact, if I move it all the way to one side, I'll recover the 1.1 kilo ohms, and to the other side, nearly zero. So 1.1 on one side, and then about 0 ohms of resistance, almost 0.005 ohms on the other. Now, if I go back and measure, say, the left two pins, I find exactly the opposite. Rotating the way that gave me the maximum resistance before now gives me the minimum, and vice versa, but always ranging between about 0 and 1.1. Let's put it somewhere in the middle. I find at one particular location a reading on the left two probes, say, of 0.70, a 0.709 or 709 ohms. Then switching over to the right two, I'll find a resistance of 417 ohms. And then across the entire device, again 1.1. So 709, 417, and 1108. And notice again, if I measure the outer two pins, that fixed value never changes. Of course, what's remarkable about this is that those two numbers are always going to add up to that total resistance across all three. Let's just try it with a different location of the knob. So I'll set the left ones, so we're at let's make it 246 ohms, and then the right two will be at about 882 ohms. And of course, 882 plus 246 equals about 1.1 kilo ohms. What's responsible for this remarkable behavior that the resistance on the left and the resistance on the right always add up to the same number? In this case, 1.1 kilo ohms. Well, let's take apart the potentiometer and find out. Grab a pair of needle nose pliers and start by removing the tabs or at least peeling them back. There'll probably be 4 on your potentiometer. Now you can remove the back of the can, and let's take a good look at what we've revealed. As we turn the knob in front, we see that a wiper blade moves across the back. Let's zoom in for a moment. Taking a closer look from the side, we see that there's a small divot in the metal ring that's bent down so that it contacts the back surface in a different location along an arc as we rotate the potentiometer. And on that back surface is a narrow stripe of thin conductive material, very similar to our pencil stripe. We see that that wiper blade goes from being closer to the left two sides to closer to the out two sides. So the wiper blade must be connected to the center pin, whereas the edges of the stripe are connected to the outer two pins. And that's why the outer two never change resistance, always giving 1.1 ohms, whereas the position of the wiper determines what fraction of that resistance is on the left half versus the right half. Placing the wiper blade in about the middle should yield about half the resistance, around 0.5 or 0.6 kilo ohms. Make sure you take your own potentiometer apart. It's so much more believable to hold it in your own hands and see how the mechanism works. And notice how you choose where the wiper blade goes, and therefore what the resistance is between two of the adjacent pins. Bringing back out our pencil stripe, we can see a direct analogy. When the probes are, say, on the left-hand side, so the red is now, say, the center pin, and the black probe is on the left pin, I see increasing resistance as I move farther away and closer as I move closer together. If now the middle pin is represented by the black probe, and the red pin represents the right side, once again, closer together means less resistance. And so that's how the potentiometer works. Go ahead and reassemble the pot, keeping in mind that anytime we've taken something apart, you really have to check and see if you have managed to not break it permanently. So fold the tabs back in, but then go back and measure and see if it's still working as intended. Move smoothly. Let's check with the multimeter again in resistance mode. Uh-oh. It looks like the process of taking apart and putting them back together must have shorted out a bunch of the leads. Rather than try to fix my broken potentiometer, I'm just going to make sure that I throw that away in the trash and grab a fresh one. And now we're prepared to use it to make a variable resistor in a circuit. I'm going to repeat the circuit that we had made last time with the LED, but now replacing the fixed resistor with the potentiometer, where just going in between two of the adjacent leads will give us a variable resistance. I suggest using the technique that I showed you last time of following along with a finger over the actual wires and the circuit diagram at the same time to make sure that you get the wiring correct. For clarity here, I've tried to use more or less the same colors of test leads that are given in the textbook. Remember to get the LED in the proper direction with the long leg always facing towards the positive end of the battery, and start with the potentiometer in the middle. If you do this, the LED should come on pretty bright, and then you should be able to adjust the brightness by tweaking the potentiometer off that middle position a little to the left and right, watching it go dimmer and brighter. But if we sweep it too far, we'll find that at some point it'll get really bright and then it won't work anymore. We've blown the LED in our circuit by putting too much current through. Because remember, we get a resistance of almost 0 ohms, a short circuit, we turn all the way to one side. So that LED, I fear, also needs to go in the trash can, along with the potentiometer we ruined earlier this lesson. But we've got a whole bag of LEDs, so let's grab another one, but this time inserting a current limiting resistor into the circuit. And for that purpose, we'll use the 470 ohm resistor. Again, that's yellow, purple, brown. Again, putting the LEDs with the long lead towards the positive side and the short lead towards the negative side of the circuit. We will now never have less resistance than 470 ohms, even when we turn over to the brightest setting. And so now we can tweak the brightness of our LED without worrying about sending too much current through and damaging it. Let's investigate a little bit more what's going on with our circuit using a voltmeter. Now, probing a circuit while it's running is something we use all the time with our voltmeter, but it's important that it be in volts mode. Never measure the resistance of a circuit when it's powered up, only measure the voltage drop between 2 points. First, we're going to show you how this works, and then we'll explain a little bit. Again, making sure you're in a reasonable volt setting, say the 20 volt scale. Place the two leads across the two leads which you chose to put in your circuit, that is, the ones which are going over to the LED. And let's see what happens with the brightness of the LED versus the voltage reading as we turn the potentiometer left and right. You should see, perhaps surprisingly, that the LED gets brighter when the voltage across the potentiometer goes down. And that as the voltage in the potentiometer goes up, the LED actually gets dimmer. Let's think about this for a moment. The first thing we have to understand voltage is that it's a potential difference. That means we're always measuring across 2 points in a circuit, say using the red probe in the V setting and the black probe in the COM port. And the voltage is always measured in reference to that COM port. So even if, say, our reservoir tank, or for that matter our battery, changed its absolute voltage with respect to some other location in the circuit, the location between the red and the black probes, that difference would remain unchanged, and therefore we'd always have the same voltage reading. It's only if, say, our battery starts to change in voltage or some other circuit component, as we saw in the short circuit. This happened, for instance, because we actually lost charge, but there'd be plenty of other reasons why a component might change as well. Then, in fact, the distance between the probes would change, meaning that the voltage we were reading, that is the pressure that electricity was being forced through with the circuit, would change as well. The next thing we have to think about is how voltage differences change as you go around a circuit. Now, the negative terminal, in fact, is usually what's called common or ground, a huge reservoir of charge, of course drawn here as water in our water model, and it's pumped up to some high voltage inside a reservoir like a water tower. Now, in order to make a circuit, we have to add some components. Here's the symbol of a light-emitting diode. We'll become familiar with this one at the bottom with its negative terminal towards, that's the shorter wire, towards ground. Now we've opened up a small hole and put in a small diameter pipe and start to take water a little bit out of the reservoir, and we find out that our LED lights up just a little bit. The small pipe limits the current, and that small amount of current due to that large resistor results in just a dim glow of our light-emitting diode. What's the potential difference in the circuit? Well, across the small pipe is most of the pressure change. The LED always has a 2-volt drop, and so most of the pressure difference is from that small pipe that's constricting the flow. What if we change things and now put in a much larger pipe, say double the size, that is half the resistance? Now we get a lot more flow through, and our bulb glows a lot brighter. And in fact, there isn't very much pressure change anymore in the large pipe, and therefore lower voltage across the resistor, which of course is what we've been measuring across our pot as we increase the brightness of the LED. Let's take one more look at this surprising result, somewhat surprising result, using the FET circuit simulation for DC circuits. We'll take our battery, replacing the water tower, bring a wire, which, remember, a wire has almost no resistance, and so it's like a huge pipe for electricity, and then we bring in a resistor. Now notice the resistor code is followed on the FET simulation, and although we don't have an LED, we do have light bulbs. This in general means we're going to be seeing lower resistances and greater currents in these simulations than we would with our LED, but qualitatively the idea will be there. So we've again placed our light emitter, in this case a light bulb, after the resistor in the circuit, and set the flow of electron currents to conventional. And now as we change the resistance, we will of course see the brightness of the LED change. And particularly as we increase the resistance, we see the bulb get dimmer and dimmer. And the current flows slower. As we reduce our resistance again, our bulb gets brighter and the current flow picks up. Let's grab our voltmeter and measure across 2 points in the circuit. We'll choose the resistor, that is the 2 leads of the pot, just as we did in the actual real-life experiment. Here we are measuring a voltage of 4.14 volts. It happens to be a 9-volt battery that's set. And let's again change the resistance and see what happens. Dropping the resistance, we see our voltage go down, and increasing our resistance, we see our voltage go up, the same as experiment. Again, as we increase resistance, there's less current, and the bulb gets dimmer. More of the voltage drop is across the resistor. Reducing the resistance, we see the resistor has less change in the voltage across it, while our bulb is getting brighter and brighter because the current keeps increasing. We will continue to explore these ideas of voltage, current, and resistance in the second part of Experiment 4, which will be in the next lesson. Here's your Experiment 4A assignment. There'll be a separate assignment for Experiment 4B next. Remember, first of all, to throw away your burned out LED, as well as your potentiometer after following along in the experiments. Make a table in your logbook recording the potentiometer readings with the potentiometer just by itself, not powered up, your voltmeter in resistance mode. Just like in the video, measure the resistance between the left center, right to center, and then all the way across, left to right resistance of the potentiometer. Make sure that they add up in the way you expect, and keep a note of all that in your logbook. Finally, we have a design project for you. In the video and in the textbook, the potentiometer moving clockwise increases the brightness of the LED. Try to build a circuit that does the opposite. That is, it increases in brightness when you move it counterclockwise. When you move it clockwise, of course, the brightness goes down. Describe and explain your modified circuit in your logbook.